In this video, I'm gonna present my topics 5 through 12 and talk about my calculations problem. First problem covered topic 5 and 6, internal flow and pump analysis. I have a centrifugal pump that deliver water at 20 degrees from an open storage vessel with a 1300 gallon per minute rate. And here's a picture that I have for that. I want to determine the quantity of liquid delivered and also the time taken before the cavitation occurs. I have the NPSH required. And after that, I'm adding a 500 feet pipe to deliver the water through a farm and examine and discuss about the internal flow. So the assumptions that I take here is that a flow is following streamline, is steady and incompressible, no work or heat transfer in this system, and the volumetric flow stay constant, and we use the standard pipe schedule for the steel in this question. So the equations that use is the Bernoulli equation with the friction, and the equation for friction and the NPSH available, and as well Reynolds number equations too. A quick look at the solution. So I'm having point 1 right here and point 2 here. Use a extended form of Bernoulli to find the friction for that, and after that we can find the best place for the pump to be displaced on the system, and we can find the volume delivered and also the time taken. After that, I'm having point 2 at the pump and point 3 at the end of the 500 feet pipe. I'm writing a extended form of Bernoulli equation, and we have the maximum allowable pressure drop during this 500 feet. So we do the try and error to find the best volumetric rate that it can use for this question in order to we not exceed the maximum pressure drop. And at the end, I'm asking for what should be the volumetric flow look like to have a laminar flow, because in the regular case we have a turbulent flow. Next question, it's the topic 9, the compressible flow, and I have a question that air enters a diverging nozzle at 1.2 megapascal and 298 Kelvin with an negligible velocity, and we want to know what is the pressure and also the velocity at the exit. So we have the Mach number given and pressure and temperature, and we are looking for the pressure and velocity at the exit. We assume air is an ideal gas and flow is isentropic, and inlet condition and stagnation condition are the same, and also the Mach number at the throat is 1. I found the properties from table A13 and table A1 for air. The formulas that I use is that C, the speed of air, is the square root of K RT, and the Mach number is velocity over speed of light. Quick view on the solution. We have the figure here. We have the velocity at the enter is about 0, and from table A13 we have K and we have the Mach number at the exit, so we can have the P over P naught value, and with that we calculate the pressure at the exit is 209 kilopascal, and we have Mach number, we can calculate the speed of light C, and we can get the velocity at the exit as well. Next topic is topic 8, external flow, and I'm examining the drag force when someone do the parachuting. So when a 70 kilogram guy parachute from an airplane and jump out, I explained that when they just jump, their weight due to gravity is way more than the drag force, so they accelerate and the velocity increase. After some time, the velocity is equalized, and because the drag force and gravity is equalized, and that's the terminal speed. It's a free fall happen. And when they open the parachute, because the drag coefficient increased, the drag force increased, and their velocity decreased a lot. So I assume airflow is steady and incompressible, and we have the area of the body given, area of the parachute given, and we consider the parachute like a hemispherical shell. Got the properties of air density and acceleration gravity, and we got the CD, the drag coefficient, from a outside reference. The formula here is the Reynolds number and the drag force formula that we used in here. Take a quick look on the solution. I have the maximum velocity, that it's when they jump, and after the time that it's equalized, the drag force and the weight. Also, I calculate the V impact when they hit the ground. They open the parachute, and I said that it's gonna result to the very low velocity, and it's a turbulent flow as well in here. Next topic is a flow through porous media, and I have a coffee machine with a coffee filter in there. I assume that coffee is Newtonian fluid and the coffee machine is full to the top. Volumetric flow stay constant and flow is incompressible, no work or heat transfer happens. So we can write the Bernoulli equation. We got the properties of that from handout 1 mostly, because we can say the coffee is almost like water. Take a quick look on the equations. I have a Bernoulli equation and hydrostatic equation, and also I have the superficial velocity equation and Reynolds for the porous media. Take a quick look on the solution. I have the Bernoulli equation, the extended form, and I found the friction in that case, and we have all the information. We have the diameter of the particle and like viscosity, density, and the epsilon as well. So we can calculate the superficial velocity, and also the Reynolds. We can calculate that here is a turbulent flow as well. The next question is the Navier-Stokes equation, the microscopic mass and momentum balance and boundary conditions, and also numerical solutions and finite differencing. So I have a pipe and it's on the angle, and we want to find a x velocity profile for that. So we assume that the flow is steady, incompressible, and laminar flow. It's a Newtonian fluid. It's a fully developed stream and infinitely long round pipe. No applied pressure gradient, and flow is parallel and axisymmetric, and no rotate on that. We assume no split at wall for a boundary condition as well, and the center line of the pipe is the axis of symmetry, so no flux at the center as well. I got the properties from handout 1, and I got all the equations from the cylindrical coordinates equation of motion on handout 9. And take a quick look on the solution. So I have the continuity equation and simplify that with steady state, no UR or no U theta. We get the continuity equation result here. And we have the x component of the incompressible Navier-Stokes equations as well. We simplified that. Twice we have to integrate and apply the two boundary conditions that I have it here: no flux at the center, and also no slip at the wall, no split at the wall, no slip at the wall, sorry. And we get this formula at the end as the velocity profile formula, and I asked to calculate the velocity at a place like in the middle of the pipe, and also here's the finite difference thing to find the expression for ux. Thank you so much.